Okay. Again, a very good morning to all of us. Thank you, Associate Professor Dr. Zunarani Jimat from Department of Biotechnology Engineering, International Islamic University in Malaysia, and to all the participants from Institute Teknologi Bandung and also from other institutions as well. Today we have a guest lecture for the Principles of Bioproduct Separation entitled Application of Superpro Designer in Bioseparation will be given by Associate Professor Dr. Zun. So this guest lecture will be carried out for 2 hours, 1 hour for the presentation, followed by 1 hour for the question and answer. So without further ado, I would like to invite Associate Professor Dr. Zun Noraini Jimat. Before that, I would like to briefly explain the outline for the guest lecture today. Next slide, please. So the opening guest lecture by me, and then we'll have presentation by Associate Professor Dr. Zun. We also will have the photo session followed by question and answer, and then closing by the moderator. And then next slide. So I will briefly explain the background of the speaker. So Dr. Zun obtained her PhD from the Newcastle University, United Kingdom in 2011, and then her expertise is in microbial fermentation and immobilization of cells and nanofiber. Her research interests particularly about synthesis and characterization of nanofiber and bioprocess design and optimization. We hope that with the expertise of Dr. Zun, students will be given a very good overview about the bioseparation process, particularly about the application of Superpro Designer. With that, I would like to provide the time to Dr. Zun to provide her guest lecture today. To Dia, could you please help with the presentation by Dr. Zun?
Okay. Assalamualaikum everyone and good morning. Thank you to Dr. Yusof for inviting me for this slot on the application of Superpro Designer in bioseparation processes. I'm sure some of you have heard about the Superpro Designer. It has been used for the class. You can simulate the separation processes using these tools, software. So at the end, you may know the overall process where you can get the information like material balance, energy balances, and also the sizing of the equipment, the overall cost of the plant, and also about the scheduling of the processes. May I know any of you have used it before, this Superpro Designer software? Anyone?
Next.
Anyone? Sorry, I'm asking to the listener while giving the lecture. I'd like to ask either any of you have used it before.
Students, you may unmute your speaker and answer the question. Any representative would like to answer the questions, you are allowed to do so because the speaker is asking questions. Any representative would like to answer the question?
Anyone? Okay, might be they just started the engine, I think. So I think I may proceed the lecture. Yeah. Okay, the next slide, please. Okay, I'm sure that you must know that in producing a bioproduct is not easy. It needs to be gone through few steps until it can be used or consumed by human. Okay, here I'd like to show to you that the goal of the downstream processing for byproduct, there are four factors that you need to consider. First, purity. You have to maximize the purity of the product. The time, minimize the processing. The yield, minimize the losses. And the cost need to be minimized. And it must be reasonable cost to develop the plant design. So means that in producing the bioproduct, the challenge is you need to have the efficient and economical process to recover high purity of the biochemical product from a complex mixture. It's complex because it's been through the fermentation process, and due to the complex structure of the biomolecules, you have to remove the impurities, contaminant, which might have similar physical and chemical properties. Okay, I'd like to ask the student, why do you think the purity, the time, and the yield and cost are very important in bioseparation processes of the bioproduct? Anyone here can answer me?
Hello. Is my voice?
Yes, I can hear you.
Okay. I think I will make about my opinion about why the high purity, the time is very important. I think that we need when we do when we do a design of a reactor, or maybe to make separation to get our objective of doing that thing of the design is of course for the higher purity or the higher yield that we can how do I say so we can get high purity and the higher yield, of course, because that is the most important objective of when we are making when we are designing the reactor that we need to use by, even though maybe it's just a theoretical, but maybe that we can use that to where we can how do I say? Maybe we can use that theoretical thing so that we can.
It's like a benchmark, you mean?
Yes, a benchmark to make so that we can, we can see, oh yes, this will be the design that we will use to when we are making the reactor that we need to get the higher purity and the higher yield with the different time and that.
True. What you say is true. That's why in production of bioproduct, we do have the bench scale, the pilot scale, and the large scale. So we have to try step by step before we go for large scales, because large scale might need a high cost, then we need to minimize the processing time, but we have to achieve high purity and high yield. Right? Okay, so I go to the next slide. Okay, so when you do the bioprocess design, there are 7 questions that you need to answer, because for bioprocess design, you have to be clear what are raw materials and utilities that you required, amount resources, the size, the total amount of resources consumed per year, what is the required size of process equipment and supporting utilities, the cost of the capital investment, the manufacturing cost, and you have to think in the case of when you run the process, if you have to stop for certain time, okay, due to unavoidable reason, you might think that is it the existing facility can be used for the new plant required or any other kind of product. And you have to think about the optimum size. What are the optimum size, batch size? How long does the single batch take? How much product can be generated per year? The scheduling and throughput, the bottlenecks, which process step or resources constitute scheduling and throughput bottlenecks, and the environmental impact, what's the environmental impact, and the best alternative among the several alternative approach. So that's why as a bioprocess or biotechnology engineering student, you have learned before the material and energy balances. You have to learn the unit operation, the heat and mass transfer, and this all the knowledge you have to blend it and you have to apply in the bioprocess design. So I would like to ask any of you here, why in the beginning you have to know the raw material and how much of the raw material that you needed, and at the end how much the product that you can be generated per year. Anyone can answer for me? Why in the first place you have to know these raw materials and the optimum size?
I think I will answer. For me, we need to understand the amount of the raw materials that is optimum for the best amount of yield. So if the raw material that we have put in the input is too much or too little, the yield will not be as expected. I think that is the short answer.
True. Because at the end, you do need to do the sizing of your equipment, like reactor. If you do not know the amount of raw material and the amount of the product that you need to produce, that you won't be able to design a good size of reactor. It's not only for the reactor, it's also for the subsequent unit operation that you need to do in the bioprocess design. So this one will be related each other, because at the end, you need to know later how much the waste that you might generate from the process, and also that the cost of the equipment, the cost of raw material, the manufacturing cost, the total capital cost. So those are related each other. Okay, similar to this the scheduling process. You need to know when the time you need to mix the raw material. You need to know what for the next process, when you need to pass the output to the next unit operation. So you have to know it clearly. If not, it won't achieve and complete the cycle within the stipulated time. So you won't achieve what the amount of that you target per batch that you have that you need to estimate before. Okay, I think we can go to the next slide, please. Okay, so I think you are familiar with these 4 stages in bioseparations. Okay, in the beginning, you have to do the separation of insolubles, isolation of product, next is purification, and the last is polishing. Okay, I'd like to ask you, why these are have been proposed, the 4 main stages in bioseparation process. Why it could not be jumbled like from firstly you do the separation of insolubles, why you cannot jump to the purification process and next to the polishing? Why you have to do step by step? Anyone can answer me?
Maybe I want to answer the question. Okay, first, if we do a purification for the product from separation of insoluble, it's more than one compound or one types of product that then if we do we cannot do purification, but we should isolate the product first. Then we can we can do purification to the product.
True,
Maybe
true.
yeah, because if we do purification from the product from separation of insoluble, there is still a lot of product that we don't need. So the process of purification is not gonna be maximum. No, it's
Yes.
not gonna be optimum.
Yeah, true. Because of you do not know that that if you jump to the next step, you might later on do need extra step, because that's why you have to follow step by step. Sometimes you need to combine the process. Like for example, you combine the process of the filtration with precipitation. It depends on what kind of your product. So before you select the best unit operation to be used, you have to know what are contaminants that you need to remove, and why do you need to use that unit operation for that step, and then at the end, what's the target of the product that you need to get at the output of that unit operation. So that's why back to the goal of the bioseparation, you do need to hold that there are 4 factors: the time, the yield, the purity, and the cost. Okay, so I'm sure that you know that the first step, what are the unit operation that can be used, like filtration, sedimentation, extraction, adsorption. Okay, you can see that in this first stage, you have to remove or collect the cell debris, or you can reduce the volume. Okay, I like to ask you, why in the first step, if possible, you have to reduce the volume and you need to remove the cells?
I want to try to tell my opinion. Maybe in the first step, we need to remove the cells or reduce the volume because the product is contained in the cells, So we need to homogenize the cells so the product can go out and we can do the next step.
Okay, I have to correct you. So in this case, if we said that we have to remove the cells, cells might be our waste. So if unless that you recover the cells, means that your product is intracellular. So in that case, you have to go to the next step, which is homogenize, or you have to disrupt the cells using the bead mill, the high pressure homogenizer. Okay, so okay, I you have to know that I'm sure that you know the byproduct might be intracellular or extracellular. If we remove the cells, means that the product is extracellular. If we recover the cells, the product is intracellular. Then we do need another step, which is lyse the cells. Okay.
Okay, ma'am. Thank you.
We need to reduce the volume because it's easy for us to control the process. Because if you process in a large volume, you might need a large unit operation, because you need to cater a large volume. That's why you need to reduce the volume, and at the end you might get concentrated product. Okay, so then the next step is isolation product, where you can use the ultrafiltration, the adsorption. Okay, where here also you try to remove materials that have properties slightly different from those desired of your product, and then purification, like chromatography and crystallization, and the last is polishing. Okay, I'd like to know you. I'd like to ask you, is it polishing applicable for all processes in manufacturing of bioproduct? Is it necessary to use it all the time, polishing? What do you think?
Ma'am, I would like to answer the question.
Okay.
Maybe for my opinion, the polishing do not need if the purification in the step purification, the purity that we need is already achieved. So we don't need the polishing step.
Yeah, true. But another additional point, if in the case that you have to produce your product in dry form, you do need to do the drying process or crystallization process. Like for example, you produce a capsule, right? Capsule or any kind of or a powder form product. So you need to perform the drying or crystallization process. If not, it's just enough up to purification step. Okay. Okay, can we go to the next step? The next slide, please. Okay, so before we go to the Superpro design, I'm sorry, I do not simulate it in through this lecture. I just show to you the theory part. Maybe later on I can show to you the real how to run the simulator Superpro design. Okay, so you can see that the overview of typical biologic manufacturing process, right? This one is in the case that where you produce the product from the cell culture. Okay, you can see that the steps are very long actually. You have to get the cell from the bank vial, you do the spinner in the shape flask before you go for the bioreactor and further to the large bioreactor. And now you can see that they remove the cells through the centrifugation or the depth filtration. Okay, then you do the harvesting, and then you start to do the product capture, and the last part is final purification. So in the process design, you have to design an efficient and economical process. Okay, you do have the process synthesis. You have to do the selection and arrangement of a set of unit operation process steps that capable of producing the desired product at an acceptable cost and quality. And second one is process analysis to evaluate and comparison of different process synthesis solution. And this synthesis step is usually followed by an analysis step, and the result of analysis determine the subsequent synthesis step. Okay, I'd like to ask you. Just now in the beginning, I mentioned to you about the purity of the product. May I know what are the level of purity that we set for different type of bioproduct? Anyone can tell me? The purity level. Okay, for example, I give you example, biopharmaceutical product and the food grade product. Okay, what are the purity level that we set for these two different bioproduct, pharmaceutical and food product? Anyone can answer me? The purity target, is it 100%, 90%?
Okay, maybe I'm gonna answer that question. I don't know the exact number, but I think if it's for medical purpose, the purity it should be more than 90%.
True.
And for the food product, maybe it doesn't have to be that high.
Okay, you are correct. In the case of the biopharmaceutical product, we have to set the quality of the purity up to 99.99%. Okay, because of we do not know the contaminant that present in the product might if it's not acceptable for human use, it might severe to it's not safe to be used. Okay, that's why for pharmaceutical product we have to set the purity up to 99.99%. Okay, compared to the food product, it can be 80 to 90%. Okay, for other type of product like organic alcohol or any kind of for example industrial enzyme or chemicals, the purity can be 30% to 80%. Okay, why I'm asking you here because here when you know that what are the set quality level of your purity of your product, and from there you will know what are the best unit operation or the process that you need to select for your product. Okay, if you do not know, if you don't have this target, you cannot decide. Okay, do you need to proceed the process up to polishing step? Do you need to up to purification step? So that is why you have to know until what level of your purity level of your product. Okay, so Next slide, please. Okay, so these are the processes that the option that you can refer. Okay, like you can see, you have to know first your product is intracellular or extracellular. Then from there, you can see the option of the unit operation that you can use in your process, in downstream processing. Okay, if intracellular, you have to do cell harvesting, do the cell destruction, you have to remove the cell debris, and then you start to extract the product. And you can see that if your product is in inclusion bodies, you have to do the renaturation, then you do the concentration, and then you can see that. That's why I told you, you have to know the purity level of your product. Is it low purity or high purity? Because you can see that different option of unit operation that you need to use. Okay. So in the case of extracellular, you can omit the step of cell harvesting, cell destruction, and removal of the cell debris. Okay. So next step, please. Sorry, next slide. Okay, next slide. Okay, here you can see that here you go for the process analysis. You need to know the 4 elements, which are capital investment, manufacturing cost, environmental impact, and other criteria. If you do it manually, this part, you can see that many things that you need to do. This why if you use the Superpro Designer, you'll be able to get all those information, but you have to key in certain data in the Superpro Designer in order to get all the information, like material balance, energy balances. Okay, so when you're synthesizing the bioseparation processes, you might pair the unit operation in process synthesis. For example, extraction and precipitation, and high interaction chromatography, or filtration, and extraction. Okay, next slide, please. Okay, for the next slide, you can see that here the main criteria for developing and evaluating a bioseparation processes. Okay, when you do the simulation, when you choose the unit operation, you need to consider these five factors. The product purity, okay, because some unit operation, the capacity, it depends on for example, if you use chromatography. Chromatography is specific for the preparation step. So you need to ensure that in order to get high purity of a product using the chromatography, you have to ensure that all the contaminants need to be removed first before you use chromatography. So from there, you can maximize the purity of your product using chromatography. Okay, robustness. Some unit operation are robust. Okay, like for example, centrifuge. Okay, but centrifuge, you have to choose the right centrifuge because not all centrifuge can be used in the large scale. Okay, so the common centrifuge that used in the large scale are the D-stack and the tubular. Some centrifuge cannot be used in the large scale because centrifuge depends on the rotation speed. Okay, if you increase the rotation speed, it might not safe for that unit operation. Okay, if large unit centrifuge, if you apply with high rotation speed, it's not safe, might be harmful to the labor, and also will be costly. And then the other thing is like scalability. Sometimes when in the large scale, you have to think like chromatography, the equipment are very expensive because the maintenance of the chromatography is very intensified, where you do need very laborious. Okay, need to clean it frequently. Okay, and it's not easy to scale up. Okay, but still in the pharmaceutical industry, they have to invest using the chromatography because they need to get the high purity. And then the cost of production of the related to the yield. Okay, you have to minimize processing time, yield losses, and the cost. Okay, the next slide, please. Okay, the process simulator. Okay, when you do the you perform the simulation using the Superpro Designer, you'll be able to analyze the integrated processes. Okay, in terms of the economic evaluation, the equipment sizing and costing, material energy balances, environmental impact assessment, the process scheduling, and the bottlenecking of batch and container process. I will go to you. I will share to you with you one case study. Which is the ethanol production from the corn stobber. Okay, before that, I like to ask you. I did mention to you, using Superpro Designer, you'll be able to get all the data like that I mentioned before, economic evaluation, equipment sizing, material energy balances. Okay, before you start Superpro Designer, how do you need to set the raw material uses or required in the process? Anyone here can answer me? Because you have to put some data before you use the Superpro. Anyone have idea? Okay, I give you an example. Okay, for example, you have to produce 5,000 tons of ethanol per year. Okay, how do you start to get the amount of raw material?
I would like to answer.
Okay.
In my opinion, we can use some laboratorium data to start as a benchmark and a starter for the bench scale and the small scale. Then we can input those into the Superpro as the basis idea for the scale up process.
True. Okay, you have to get some data from the literature. True. Okay. Okay, for example, I give you example just now, 5,000 metric ton per year of ethanol need to be produced. Okay. From 5,000 metric ton per year, okay, you have to know how much of the ethanol that you need to produce per batch. Okay, you have to convert first that 5,000 metric ton per year per batch. Okay, per batch you have to know first per batch how long you need to produce the ethanol. Like might be for example 3 days or 4 days, for example. So then you have to exclude the period for the start up and shutdown. Okay, because yearly surely the plant need to be shut down because of you need to do some maintenance. Okay, maintenance work. Okay, you have to exclude that period, and then you have to calculate. For example, you need to run like 30 batches per year. Okay, 30 batches per year you have to recalculate. Okay, 5,000 divided by 30 batches. So easy to calculate, might be we can use 20. So you need to run 250 times per year. Metric ton per batch. Okay, why I ask you, because at the end you have to calculate through the stoichiometric equation, okay, in order to know what are the raw material that you need to do and that you do need to produce your product. So just now I told you the ethanol. So in the case of ethanol, from the corn stobber, okay, you have to think from the corn stobber, how can you produce ethanol? Means that you need to get the simple sugar, right? Is it right?
Yes.
Okay, so how do you need to get the simple sugar from the corn stobber? Anyone can answer me?
Maybe we can do hydrolyzation of the corn stover.
True. Yes, we do the pre-treatment. So, Dia, can you go to the last slide? But the slide might be too small. Okay, in that case, you go to the slide number 20, Dia. Okay, so I give you example. This one, I could not give you the real flow diagram used from the Superpro because it's too small. I showed to you actually, but in the last slide of my lecture here, overall flow diagram, page 24, but it's too small. That's why I transformed to this block diagram. Okay, you can see that you have to sketch first, before you use the Superpro Designer, you have to sketch first the process of your product. You have to think from the beginning until the end. Okay, before I go to the real case study, I like to inform to you, to explain you one more slide before we go to case study. Okay, dear next, slide number 10. Okay, you can see here, okay, this is initial step that you need to perform using the Superpro Designer. You have to develop a flow sheet by putting together the required unit operation. Okay, you have, in my case, I prefer you to run the unit operation one by one first before you add other unit operation. If not, you might get some error, then you cannot complete the simulation. So what I mean, first step, if you do need the reactor first, you put the reactor first. You put the reactor first and you draw the line of the stream. Okay, you have to determine how many input for your unit operation, how many stream for your output unit operation. Okay, then after that, you start to register the raw material that you do need in your process. Okay, like for example, I told you production of ethanol from the corn stubble. So means that you do need the simple sugar from the corn stubble. You do need to perform the pre-treatment where from the corn stubble you have to uh, hydrolyze the cellulose or the hemicellulose in order to get the simple sugar, like for example glucose. Okay, so you have to set this all the raw material or the side product they might produce during the process. Okay, and then after you register all the material used and specify process condition. Okay, for example, the reactor, you have to set there how long the fermentation will I mean, is it 24 hours or 48 hours? You have to set the rotation speed. You have to set the temperature. Okay, you have to set all the condition. That condition is subject from you get the information from the literature review. Okay, and then you have to, from there you can start the material energy balance. This material energy balance, you have to calculate manually first what are the stoichiometric coefficient of your product. Okay, I'm sure that you can, I hope that you know, like for example, you use the simple sugar glucose. So if your product is aerobic, you do need the glucose sources, carbohydrate sources. Then you do need the oxygen, you do need, might be nitrogen sources, and then you can get your product, like for example ethanol, and you might have a side product like isopropanol, carbon dioxide, and water. That the output. Okay, you have to do it manually. Then you key in the software, in the simulator Superpro Designer. Okay, then they will run for you. Then you can get the material balance for each stream that you draw for your unit operation. Okay, then from there you for the costing, you have to set, there are some calculation actually, but I do not explain more about the costing. Okay, because you have to do some calculation in order to you have to put some data in the spreadsheet first before you can get the estimated capital investment, the operating cost, the manufacturing cost, and analysis of the profit. Okay. Okay, Dia, can you go straight to the case study? Case study is in the page of 17. 17. Okay, here. Okay, this is a production case study production of ethanol from the conserver. You can see that here already calculated. You said that the feedstock flow rate is 2,000 metric ton per day of dry mass of corn stover, which is equivalent to 4,000 metric ton day of wet biomass, and the target is 18 metric ton per hour of fuel grade ethanol. So annual production equivalent to 6,044 gallon per hour and 47.8 million gallon per year. Okay, so you have, in order to insert the data in the Superpro, you have to know the component in the constable, because if you put just constable, you cannot solve the problem. Okay, that's why you have to know the material or the component consists in the constable, which are the cellulose, hemicellulose, lignin. Okay, the top three components are that you need to key in. The rest might be neglected because it's difficult if you put the ash and other solids, because they don't have the empirical formula. So it's hard for you to get some some when you if you key in the Superpro, because they don't have empirical formula, so it couldn't generate for you the data in the output stream, and you do not know the amount of it, right? How much? Okay, so next slide there. Okay, so you can see that in this case, the constable went through two steps of pre-treatment. First is thermal hydrolysis. Second is enzymatic hydrolysis. Okay, I'd like to ask you, in these two processes, what are unit operation required in order you choose and put in your Superpro Designer? Anyone can answer me? The unit operation. Okay, if in the lab, what equipment, what glassware that you need to use for the thermal hydrolysis and enzymatic hydrolysis in the lab? Anyone can answer me? Or you are not clear with my question? Class?
Maybe the question is not clear enough because from my perspective, my internet connection is not that good. So maybe I think that's my problem. I think yeah, that's from me my perspective.
Okay, sorry. Okay, I ask you. What I ask is, when you perform the pre-treatment through the thermal hydrolysis and enzymatic hydrolysis, what unit operation that you can use for this process? Is it a simple tank, or the continuous stir reactor, or vessel? Because
Okay, I think I will answer my
okay.
question. If unit operation, that mean by like how do we say, like batch or fermentation, I think this pre-treatment can be if it's a lab scale or maybe the small scale, it can be used it can be used in the batch one, because batch is more simple, I think, for the lab, and it will not cost you much because the flowing of material that you need to do the pretreatment of I think like thermal like enzymatic hydrolysis and the thermal hydrolysis. But if in the real maybe the higher scale, maybe, or the higher scale than the lab scale, or yeah, like medium scale up to the big scale, like industry scale, it usually use the continuous reaction. Continuous reactor. Yeah, continuous reactors, because it will be more efficient, more automated because of the flowing. But even if it will cost you much, but it will give you the high efficiency and effectiveness of the pre-treatment process. I think
True.
that's
Yes, correct. You can use in the case of the in this case they actually suggest to use the continuous stir tank reactor, okay, because you have to run at high pressure and high temperature, okay, especially for the thermal hydrolysis. But here I give you example using the well mixed reactor, where in this case you have to set high pressure 10 bar at 180 degrees Celsius. Okay, so I'm sure that you know that for the pretreatment of the lignocellulosic, there are many techniques that you can use. Okay, but it's subject to the efficiency of that process and the cost of that process. So in this case, I give you example using thermal hydrolysis and enzymatic hydrolysis. You can also use the chemical hydrolysis, but at the end, you might generate some waste. Like for example, if you use sodium hydroxide, you can also use acid hydrolysis or the mechanical process, okay, using the high pressure homogenizer, using the bead mill, the sonicator, okay. So in this case, when you choose thermal hydrolysis, you need to know the unit operation. Okay, so in this case, they use. So in this case, they use the well mixed reactor. Okay, then you have to set the condition 10 bar and at 180 degrees Celsius. Okay, when you do the setting up of the well mixed reactor, you have to know the stream input for the reactor and the stream output for the reactor. Okay, so then you can see that you do need to have the stoichiometric coefficient. You can see that the cellulose plus water and get the simple sugar glucose, and some might be you have hemicellulose plus water then get xylose. So you can see the reaction extent is 10% and 70%. Those information are needed in the Superpro Designer. You have to do the calculation first. Okay, where to get this information? You have to get from the literature review. You have to perform literature review. You have to find what are the best reaction. Through the thermal hydrolysis, you can get high yield of glucose, high yield of the cellulose. You have to know what are the extent of the reaction. Okay. And similar to enzymatic hydrolysis here, you can see that in this case, the reaction extends up to 90% for the glucose to get from the cellulose and 50% to get xylose from the hemicellulose. Okay, so if not, you won't be able to produce ethanol from the corn stover if you could not get this kind of information. Okay, I'd like to ask any of you here. Since you are bio engineering student, right?
Yes.
Okay, so later on you might have the project design, right? Or you don't have the project design? Project design means that you do need to design the feasible plan to produce certain amount of the product from any kind of natural sources, and you have to do the process flow from the beginning until you get the end product. Do you have that kind of project?
I think for the, for the designing project of the reactor, I think that we have the project design as a task. I think the task, maybe the, how do I say, like we say as the last task before our graduation, maybe, I think.
Okay, so I think you are clear, right? Why I'm emphasized on the stoichiometric coefficient? Why do you need to have this kind of fraction? Are you clear, all of you? Why do we need to have the stoichiometric coefficient, the ration equation? Why do we need to have the information? I'm sorry, I could not show you a real simulation. If not, you can see why do we need to have that stoichiometric coefficient in the simulator.
Okay. Maybe I think we need the stoichiometric. It's for the program itself. It doesn't have any. The program doesn't know how the reaction works. So if we want to make some model, we should have the data of the stoichiometric, so we can so the program can simulate
Yes.
the stoichiometry.
True, correct. That's why if you normally generally in the literature review, the data that you have in the in the scale in the lab scale, so you have to do the scale up in order to match with the large scale of the process that you will simulate in the Superpro. Okay, so I'm sure that you are familiar with the yield of like product per substrate, yield of the product from the biomass. You know, right, that term, because that information also useful for you when you do stoichiometric coefficient, because I'm giving you here is very simple way, because if not, you have to put the biomass empirical formula in the reaction equation. Okay, I'm sure that you are familiar with that, which is like, for example, the simple sugar, carbohydrate, glucose, plus with oxygen, plus with ammonia, nitrogen sources, you get the biomass, your product, water, and carbon dioxide. So you can see the element of carbon, hydrogen, oxygen, nitrogen. So here, the Superpro will simulate later on all the amount of your for each component. Okay, so that's why it's very important. Okay, can you go to the next slide, please? Okay, the next slide. Okay, next. Next slide. Okay, so before you start do the simulation, you have to sketch first what are the process involved in the in your production process. Okay, you have to be clear. Like I said before, in the downstream processing, there are 4 stages. Okay, separation of the insoluble, extraction of your product, and purification, and the last one is polishing. Okay, so you have to sketch first. So in this case, I start from the because I mean from this from the I mean where you get the feedstock. Okay, from the transporter, you have to wash first the corn stobber, you have to grind it, sieve, and do and then go through the screw conveyor, and then next step will be the pre-treatment. You can see that the pre-treatment involve the reactor thermal hydrolysis, the flash tank, and the belt filter, reactor enzymatic hydrolysis, bed filter again, and then to the storage tank. Okay, so you have to sketch this first, then you have to rough idea how to design using the Superpro Designer. So I suggest when you put all the unit operation, you put one by one. you put reactor thermohydrolysis first, you key in the input data, okay, input data, and then you draw the output stream, and then you run, you simulate, okay. If there is no error, then you put the second unit operation, flash tank, for example. Okay, then you have to think, what is the suitable, appropriate unit operation to be placed for the next step. You cannot simply put that unit operation without thinking about, like for example, reactor thermal. In this reactor thermal, the pressure used is high and temperature is also high. Then why they put the flash tank? Okay, there are some reason why they put the flash tank. Because some students, they forgot that you cannot simply put a bed filter, for example, before after the thermal hydrolysis, okay? Because that filter might need to operate in the normal temperature, in the room temperature, okay? While the output stream from the reactor thermal hydrolysis is very high pressure and high temperature. That's why you need to put the flash tank, because flash tank, okay, it will condense and reduce the pressure steam, okay, and then the heat supplied heat to a low pressure supplyment, okay. That's why you need to put the flash tank before the bed filter. Okay, so in this case, why do you need two bed filter? Because the first bed filter is need to remove the suspended material, which includes the lignin, anhydrous fraction, okay, and includes the generated fermentable like glucose and xylose, okay. And the second bed filter is used to remove the suspended material as well, but 60% of the suspended material is recycled back to the thermal hydrolysis step for increased the conversion. So for each unit operation, you have to know what's the purpose of it. You cannot simply put the unit operation without knowing the purpose of it. Okay, so any question that you need to ask me?
So Dr. Zun, have you finished your presentation?
No.
Oh, not yet. So if you have finished, then we can have the photo session and the question and answer. But if you haven't finished, you can proceed then.
Might be 2 more slides, then we can finish.
It's okay. It's up to you.
Okay. Okay, I continue the next section. After pre-treatment, we go for fermentation and separation section. Okay, next slide, please. Okay, so in this case, if you can see that you do need the inoculum column and then fermenter. And here is very simple process for separation section where they use the distillation column. But in this case, there are two distillation column are required. Okay. First distillation column they use for to get the 40% of ethanol solution, and the second one you will generate high ethanol solution. Okay. So I'm sure that you are familiar with distillation column. It's just you need to know how many unit operation that you do need to get or to get high purity of the ethanol. Okay, and the last slide will be go to the page 23. Okay, these are example quite small, so sorry. Profitability analysis of the from this production of ethanol. Okay, from the simulator also you can get this kind of profitability analysis. Normally, in my case, I will ask my student to do the manual calculation first. Okay, to find the working capital cost, manufacturing cost before they key in the data in the simulator. Then from that it will simulate the result of your actual plan according to your target of your produced product. Okay, so then I think the slide number 24, dear 24, it's not really clear. This is overall flow diagram of that constable. Okay, the top left of the diagram show the pre-treatment. The bottom left diagram is for the fermentation part, and the right corner diagram is for the purification step, and the top right diagram is for the utilities. I'm not emphasized on the utilities. Utilities where you need to reuse any heat that generated from the process, and also the water that generated from the process, you reuse, recycle for your plant. Okay, water might be can use for the boiler or the steam, and the heat can use for the heat for the steam as well. Okay, and so I think that's it. I'm so sorry I do not give you the actual simulation of the Superpro Designer. But compared to SPICs, Superpro Designer is more specific for the bioproduct because they have various type of fermenter that you can use there, and they have the specific innovation like chromatography, and these are the obvious different compared to SPICs. But SPICs is more on the chemical product, where you can use different approach of the material and energy balances calculation, because you do need to involve with complex equation compared to the Superpro. Using the stoichiometric coefficient, you can have, you can simulate your fermenter or the bioreactor. So that's it, Dr. Yusuf.
Okay, thank you very much, Dr. Zun, for a very good presentation that gives an overview about the bioseparation processes in general, explaining that there are 4 steps and then the importance of every steps, and then giving an example for the Constover production system, and then how to tips and tricks to begin with the Superpro Designer, and at the end you can see these overall flow diagrams. Before we proceed to the question and answer, I believe that students have a lot of questions to ask regarding on the Superpro or regarding on bioseparation processes in general. Now we proceed to the question and answer session. So there are 51 participants, including the moderator and also the speaker and the assistants. So all of you are invited to ask questions directly. Yeah, you can unmute your speaker, and then maybe you can raise your hand. If there are so many people that want to ask questions, you can raise your hand, or I think that it's okay. You can just unmute your speaker because we don't have too much people in this session. You can unmute your speaker and ask directly to Dr. Zun. And before that, I just would like to remind you that in the chat column, don't forget to fill in the attendance form, and then from Dr. Zun, you can refer to the link for the initial simulation process. So while doing so, the students, you are allowed to ask questions.
Can everyone see the video through the YouTube?
Excuse me, I would like to ask a question.
Okay.
For the intracellular products, it was mentioned that renaturation is done after cell debris removal. Why do we need to do the renaturation process, and what is the output product of renaturation? Thank you.
Batch process. Continue.
Okay, so in that case, we need to get we need to recover the cell first. Then after you do homogenize, you will get the cell debris and your product. So debris you have to remove. Okay, why do we need to perform the regeneration? Because of your protein is intact in the cells. Okay, Yeah, here's the slide. This part. Okay, so you can see that you do need to, because your product is in the inclusion bodies, so you have to dissolve the inclusion bodies, do the renaturation, and you remove. It's like your protein is encapsulated in something in the cells. So that's why you need to perform the renaturation using enzyme or any kind of chemical. Okay, and then after that, you can get your protein. Then you have to concentrate back because it's already dissolved in the chemical or in the enzyme. It's diluted. Okay, that's why you have to concentrate using any kind of innovation like attraction or the precipitation, crystallization. Okay, so these are common process in case of your protein is recombinant protein. Okay, like for example, recombinant protein. What can I say? Example, like insulin. Yes, insulin. Okay. So is it clear? If your product is in inclusion bodies, in transfer product, you have to perform renaturation. There is common step for that.
Okay, thank you, Nadia Delphi, and also the speaker. Any more questions from the students? We still have enough time for a lot of questions. There's already one question. There should be another 9 questions to go.
Okay. Maybe, Mr. Yusuf, I would like to ask some question.
Yeah, please.
Okay. If we look at the unit procedure for each type of separation procedure, there's a lot of type, like we have batch, continuous, or maybe we have a lot kind of unit procedure. So for example, for homogenizing product or feedstock, we have a lot of option to do that. So to choose a unit procedure that we want to use for the modeling itself, or if we want to scale up our process, is that we should choose the unit procedure before we do the modeling process, or from the modeling process we can get insight from each type of unit procedure. Like we can compare from, oh, if we use bed meal, we get this much of product with this much of purity. From sonication or anything, we can get yield around this number, and the purity is this number. Or we should choose the unit procedure before we do the modeling process. Maybe that's my question.
Okay. Normally, what I suggest to my student, I ask them to find from literature review. They have to get the information, several options that they can use in their downstream processing. Okay, for example, if you see my slide, in the first stage of downstream processing, where the part of the, okay, if you can see that insoluble, when you do the separation of insoluble product, okay, there are 4 different unit operation: filtration, sedimentation, extraction, and adsorption. And all 4 unit operation here can be used to remove or collect the cells and reduce the volume. Okay, for example, I give if they choose between filtration and extraction, I ask them to justify these 2 process first. They normally I suggest them to do it to do study first. Okay, like for example, filtration and extraction. Extraction is using solvent, while filtration, it use the filter media. Okay, I might ask them first, okay, what are the component or contaminant that you need to remove? Is it based on the partition coefficient, okay, or is it based on the sizes of the contaminant? If huge difference based on the sizes, you go for the filtration. But filtration are many type of filtration. It could be the dead end filtration, or it can be the tangential flow filtration. So then they have to justify which one that you need to use before go for the Superpro Designer. Because if you go straight to the Superpro Designer, okay, for example, you straightly go for the uh, filter press equipment, for example. And suddenly when you run, you cannot achieve a good uh, removal of your contaminant. Percentage are very low. So then you have to randomly try with other unit operation. So you might waste some time. So that's why I ask my student, I ask them to justify first the pro and cons, how much of the contaminant you'll be able to remove and how much the recovery of your product. Okay, then you can justify why do you choose that unit operation. The justification is based on the 4 elements that I mentioned to you. The yield, the cost, the time, and the purity. I think in each unit operation industrial processing, it's based on these 4 elements, 4 factors, right? So that is my answer.
Okay, thank you for the question and answer. Next question from the students.
The result,
Yeah.
can the student open the YouTube link that I shared just now? Because there you can see clearly how they start do the Superpro Designer. When I told them that here you can choose either the, can you ask Dia to click on that YouTube link?
Yeah. Yes, I've already clicked that. Maybe Dia, can you click and perhaps start sharing the video in YouTube?
Yes, if possible. So the student can see actually via the Superpro Designer, you have to choose either the operating mode is batch or continuous. So it depends actually what kind of your product. Some process you can run batch process, some you can run continuous mode. Okay, so you can see that in the first stage minute 2.42. You can see that you have to choose first is either batch or continuous. Okay.
Okay, I will play now.
Yes, please.
This is part 2 of the Superpro Designer video series that covers the tutorial that can be found in Chapter 2 of the Superpro Designer manual. Please make sure to watch part 1 of this tutorial before proceeding with this video. Also, remember to visit our website, www.com, where you can download an evaluation version of Superpro Designer.
Yeah, proceed to minute
Therefore, the next step in the model is to initialize the operations that were added to the 2-unit procedures. Let's begin with the reactor. To access the operations, select the unit procedure, right-click on it, and select Operation Data. Let's begin with the first operation by clicking on it. Through this dialog, you can access or modify the simulation data for an operation, such as the operating conditions, scheduling data, emission specifications, and labor-related information. To initialize this operation, let's begin by selecting the stream that we'll use for the charge. This is done by using the drop-down list at the top of the tab. For this operation, select the stream named heptane.
I think this is the part 2, right? The part 1 is what I mentioned. Okay, I posted just now. Can you see that? The one that you show is part 2.
Batch process.
Okay.
Continuous process modeling will be discussed in a separate video. Also, if you'd like to follow along with the model but don't have Superpro Designer, please make sure to visit our website www.intelligent.com, as you can see on my screen, where you can download an evaluation version of the tool. In addition, you can also download the full Superpro Designer manual and several papers that discuss the tool through the literature page.
Dia, can you forward a bit to
Corresponds to the example presented in chapter 2 of the Super.
Yes.
242?
42.
242. 242.
Oh.
242.
Operating mode dialog appears.
Okay. You pause there. So here what I mean, batch and continuous. Okay. And then you forward a bit on okay, you forward to 334.
334.
Okay, so you can see here this you need to register the component of the that you required for your action. Okay, so probably Dr. Yusof, student can study from this free YouTube Superpro on the Superpro Designer website. Okay,
Yeah.
to the
Okay.
YouTube. Okay, can see clearly how to run the simulator Superpro. Okay, so now probably they would like to ask any other question. Okay.
Yeah, okay, thank you, Dr. Zun. So students, you may check the www.intelligent.com. There is a tutorial of how to use the Superpro for beginners. So any further questions? I believe also there are several students who have used Superpro for their case study to draw the process flow diagrams. Maybe there are questions of how to use it properly for beginners, perhaps. Maybe to Nadia Yasmin, as far as I remember that she's from the group that use Superpro to draw the process flow diagrams. Any difficulties when you try to use Superpro?
Yes, I actually have a question, but to answer my use of questions first, I did come across some difficulties in which I am not able to do the simulation yet. My application was limited to the process flow diagram making, so I wasn't able to do this simulation. Right now, I'm still a bit confused how we can do the input of the materials and how to do the overall simulation. And to add to that, I also have questions regarding the lecture. So if we were to not satisfied with the economic evaluation result and we want to minimize processing time, cost, and yield losses, should we directly modify the input or flow rate on the unit operation, then redo the simulation? Or is there a method that we can use where the program can predict the best input and design so that we can get the lowest cost of production possible? Yeah, so that's my those were my questions. Thank you, Pak Yusuf.
Right. So there are three questions, if I remember correctly. First is she's still not clear how to put the input and output, and second is how to run the overall simulation. Maybe because she hasn't tried yet completely. And third question is if she's not satisfied with the evaluation or the results of the simulation, what should she do? Whether she immediately adjust the input or adjust the conditions, or what are the tips and tricks perhaps to modify the results of the simulation so that it fits the desired value? Perhaps to Dr. Zun, can you help to answer that question?
Okay. For input and output, for the initial unit operation, you have to determine first what are your input. Okay. What are the main components that you need to fit to the unit operation? Okay, the simple is the reactor. So surely you do need oxygen, you do need carbon sources, nitrogen sources, and then the output. Normally there are two streams. One is you need to push out the gas, and the second one is the output of the biomass, where is in the biomass it consists of all kind of the product that might generated from the fermentation process. Okay, then for the subsequent process, okay, for example, you put the centrifuge. Normally centrifuge may have only two output. Okay, input one stream for the centrifuge. So for the output, for that centrifuge, one is the solid, the other stream is liquid. So in order to determine the input and output, it should be logical subject to that unit operation. Okay, for example, distillation column, only two stream, bottom stream, up stream. But sometimes students are confused if the bottom stream have many component or product in the bottom stream. Surely they have many components because it subject to you have to be clear in the process of your product. Okay, because like for example distillation column, if the component have a lower boiling point, they might be goes to the bottom stream. So it might be varies of the product where you are not be able to remove it initially. Okay, so that's why if I give you example just now, the constable, you do need two distillation column because probably in the first distillation column you will be able to remove similar desired characteristic of the product from your targeted product. So might be it's exit in the same stream of your product. So again, you do need another unit operation. So it depends on that unit operation. You have to know that clearly that unit operation have how many input stream and output stream. It's not logic if you have like bioreactor, but you do put like the output like 4 to 5 stream. I mean in the real bioreactor, you normally have one output where you collect your sample. That sample is the fermented media that consists of many components in that biomass culture, right? So then you do the centrifuge, you might get the pellet and the liquid, right? So they have two stream on that. Is it clear? What's the name of that student?
Nadia Yasmin, is it clearer now with the answer from Dr. Zun?
But I only answer first question. Okay, the second question, the run overall simulation. You have to run one by one unit operation. You cannot put several unit operation that you run simultaneously. No, because if not, you cannot detect where the error comes from. Okay, so you have to, for example, you put the bioreactor, you have to run first, see the output. If you can generate the data in the stream, the output means that the run is successful. If you then you put the subsequent unit operation, you run again. Okay, you cannot put simultaneously 4 unit operation at one time, then you run. Cannot. You have to complete one unit operation, run, and then you put the next unit operation. And the third one, unsatisfied simulated result. Okay, yes. You have to put what can I say? Trial and error. Okay. Sometimes we cannot get 90% recovery of your product. Okay, it needs to be logical. Even in a real plant, they won't be able to get the 90% conversion. Still, like in this example, for example, you like to get the simple sugar glucose from the cellulose. I show to you that the enzymatic hydrolysis is able to get the conversion up to 90%, unlike to the thermal hydrolysis. So it's either you add another unit operation or you return back the recycle stream to the unit operation before and you try to run again, can you get a good yield or good conversion? Okay, you have something you have to try and error. There is no like solution for that. Okay, you cannot find it. Okay, you have to. That's why we engineer, we try to find the solution to get the I mean answer for any kind of problem. Not any kind of problem, for certain problem. Okay. Okay. Thank you.
All right, thank you, Dr. Zun, for the answer. So I hope that Yasmin has a better view now about how to use the simulation to get the desired results. Angelica Williana, she has raised her hand. Please, you are allowed to unmute your speaker and ask question.
Thank you, Pak Yusuf. Good morning, everyone. Good morning, Dr. Zun. Thank you for such an insightful session. I've learned a lot and like the general concept of using the Superpro. However, I am really new to Superpro, so I might have these questions that are very basic. I really hope that you can help me on this. So first question is about, I had this project with my friends in reviewing a journal on beet milling, and I see that the Superpro has also the unit for beet milling, but we learned that there are some properties that correlates to the whole process of beet milling, as in, for example, the size of the beets, the agitation, and all. So my first question is, can we like customize our units to that kind of like properties within Superpro? And my second question is about your presentation. I saw that you mentioned about the how Superpro could actually help us in calculating the environmental effects of our unit processes. So is there any like an exclusive alarm or like an exclusive equation within Superpro that could actually like notice us and whether like certain output is like way way bigger than it's supposed to be, or is it something that we have to calculate manually at the end of the day? That is all. Thank you.
All right, thank you, Angelica. So there are two questions. First is about the beet milling. Can she customize the parameters in the beet milling? And then second is regarding on the environmental impact. Are there any alarms so that we know that these are way above the limit, or that we have to read the results and then justify the results ourselves? So Dr. Zun, can you please answer that question?
Okay. In the case of beet milling, is very rare in industry. People use the beet mill actually in the process, but I do not know whether you come across where the beet mill can be used in the large scale. If can be used, is good because normally the problem with the beet mill, when you do process, it might some debris from the beets where it can damage your product. Okay, so it's very rare in industry. They choose the beet mill. That's why I told you in the beginning, you have to justify why you use that kind of the beet mill. It's not because of it's available in the Superpro only, but you have to know why pro and cons of using that unit operation. Okay, but anyway, if you insist to use the beet mill, probably it is ball mill. Okay, I mean, like what you mean, the size of the beets, the agitation. Even I could not tell you what the appropriate size or the agitation speed for your particular case study, because in that case you have to know the amount of the product that you need to process and then you have to back to the theory part how to design the ball mill. Then from there you might know the size of the bits and the agitation that you need to use for your bit mill process. Okay. I don't have the more details information about the designing of the bit mills. Probably you can try to find it, but if I can find it, I let Dr. Yusuf know and let Dr. Yusuf let you know. Okay. And uh, about the simulation data, like it's like an alarm whether it can tell you it's something you need to limit for the simulation process. I never come across on that, so I do not know actually. But as I can say, like for example, when you set a certain condition for unit operation, it needs to based on the guideline from the, what can I say? For example, when you do the thermal hydrolysis of your lignocellulosic, if you put high pressure and high temperature, it will be, you have to check first, is it suit or not? How to check it? You have to back to the literature review, because I couldn't say to you what are the range of it, because I'm not practicing on the side, okay? But as I said, as engineering student, we learned it before in our thermodynamic class, in fluid mechanics. So we have to apply back, okay? So there is no specific answer for that. So I'm sorry for that. For environmental impact, I'm not really do the analysis of the Superpro Designer on this aspect. But I do know that I just normally I just ask students, like for example, I will observe from each unit operation that they simulate. I will see the stream output where the one that they discard. I will check the amount of water, the amount of the unwanted chemical, or any kind of unwanted or contaminants. I may ask them, okay, what you are gonna do with this component, this product, okay? Because this is common question by the examiner when you present your simulated result. They might ask you, what are you going to do with the sulfuric acid that been discharged from the stream? Okay, you have to think about that, about the water. Okay, the limit amount, I think, to run, like for example 5,000 metric ton of ethanol, for example, surely you will generate high amount of water, higher amount of other contaminants. Okay, you have so surely you need to do something with that kind of waste generated for that plant. Okay, so I do hope that you clear on that. If you are not clear, I try to dig it again. Okay, because that is normally I do for my student project. Okay, so probably if I have any other extra information, I will let Dr. Yusuf know and ask him to tell you. Okay, thank you.
Okay, thank you, Dr. Zun, for the answer. So yeah, it is very important to know the environmental impact, and we can check it manually whether it exceeds or whether it's within the specification of the environmental requirement. For the next question, we have Rania Hana Rafifa. So Rania Hana Rafifa, you have raised your hand. You may ask your question.
Okay, good morning, Mr. Yusuf and Dr. Zun. I want to ask about regarding the Superpro Designer. Currently, I had a difficulty to install the Superpro Designer because I was using Mac as my main OS. So the app is incompatible for the Mac. And could Dr. Zun or Mr. Yusuf suggest me about the alternative for Superpro Designer for Mac? Thank you.
Oh, okay. I'm sorry I could not answer you for this question, but I may ask my friend because my friend used Mac to run his Superpro Designer. Then I will let you know later through Dr. Yusof.
Okay, thank you, thank you, Dr. Zun. So there should be a different version for Mac. We will let you know about the suitable version for Mac. Any other questions? Okay, from Mariam Aziza.
Okay, thank you for Biosef and ma'am. Okay, what I want to ask is how to model with Superpro for case precipitation using salt. As far as I know, when we're using salt in industrial scale, it's consume lots of money and lots of salt, of course. So we would like to firstly analyze this for pilot scale. Does Superpro should be only for industrial scale? Thank you.
Oh, not necessary. You can do for the pilot scale as well. So I think you should know the limit for the size for the pilot scales and the size for the industry scale. I forgot what's the ratio. Pilot to industrial scale. But surely not for the bench scale lah. So for the pilot scale is possible. If you like to up to pilot scale only. I think there is ratio for that, but I forgot the ratio of the pilot scale to industry scale. But it's possible the pilot scale as well.
All right, thank you. So there is a ratio, yeah, for conversion from pilot to pilot scale to industrial scale, but it's also the ratio can also be used, yeah, for early estimation. For the next question, Rizky Pradiatama, you may unmute your speaker and ask question directly.
Yeah, thank you, Yusuf, for the time. And I want to ask about the presentation. In your scheme in fermentation, if I'm not mistaken, you tell that we must do or we must go through the storage tank before do the distillation column unit. And I want to know why we cannot just go to the distillation process without the storage tank unit. Thank you.
It's because of sometimes when you run in continuous process, for example, sometimes you do need some gap time for the next process. Okay, and sometimes the decision column they have their limit capacity. It cannot process in a bulk amount probably. Okay, so that's why you need to have a storage tank before you go to the next step, like for example decision column. Okay, so even though it continuous process, it still need a storage tank. Is it okay with the answer?
Yeah, thank you so much, Dr. Zun, for the helpful answer. Thank you.
Okay, thank you, Rizky. And the next question from Mufid. You may unmute your speaker and ask question directly to Dr. Zun.
Okay, I would like to ask question, Dr. Zun. From the application itself, we can, from the unit procedure, if example, we choose a culture cell, then there's a lot of unit procedure. We choose one, example, bioreactor. Now, in bioreactor, there is a lot of aspect that we can fill in it, like equipment data, equipment content, and there's a procedure data, operation. Now, what make I'm interested in the operation one. In the operation, there is a lot of available operation. So actually, there's an operation sequence. Show what we should do, or what is the operation sequence in when we use the bioreactor real uh, in real one, not the modeling one. So yeah, what is the operation sequence effect to the model itself? Thank you.
Okay, do you mean that how we set up the process sequence of that product? Do you mean that?
Uh, if we look at the unit procedure, there is add or remove operations, and there is a lot of available operation like agitate, charge, cool, crystallize, distill, evacuate, and etc. What that sequence affect the modeling system that we make, or is just for like without, yeah, that's
Okay, okay. What do you mean that the stages like I showed to you the 4 stages? Do you mean that we do need to follow step by step or what? I'm not clear with the question actually.
from example from one procedure, if we use example, we use filtration.
Yes.
In filtration, we got example, we use microfiltration. In microfiltration, we got or maybe we got like flash, hold, SIP, concentrate, CIP. That operation,
Oh, you mean the operation for the unit operation, you mean?
yeah, yes,
Oh, I
yes, yes.
see. So that is, as I said, is subject to the unit operation that you use. What the objective of the unit operation? The CIP, SIP is for this cleaning in process and steam in process, because some equipment you do need to do that process.
So, what does it affect to the modeling result, or it just we tell how the unit do?
Okay. This is specifically for the product that required high sterilization condition. Like for example, when you produce therapeutic protein, for example. So you do need to put the condition for SIP and CIP, but not all for the unit operation. Okay, so I could not get okay. SIP and CIP. It's not necessary for all equipment actually. As I said, it's subject to if you require when you, like for example, when you do the chromatography. Chromatography, once you have been used in the process, you have to do the CIP, cleaning in place, where you cannot, because it's large scale, you cannot pull out the membrane filter and clean it manually. No, that's why you have to put CIP, cleaning in place. Steam in place, SIP is where, like for example, steam in place. Okay, for bioreactor, fermenter, you cannot pack the fermenter in the autoclave. So in the simulator, that's why they put SIP, steam in place, because before you feed the media, before you feed the all the components required fermentation, you have to do the steam in place. You have to do sterilization. So sterilization condition is the common temperature 120 at I think that's 10 minutes. Okay, so that is simple way that you can set for that particular unit operation. So it depends on the unit operation. Okay, it's not necessary for all.
All right.
Okay, thank you.
Yeah, so hopefully you're clear about the CIP and SRP depends on your products. Okay, the next question from Kevin. Kevin, you may unmute your speaker and ask directly to Dr. Zun.
Thank you, Pak Yusuf. And hello, Dr. Sun. I would like to ask about the technical research of Superpro Designer. So I have the problem to design the process we need to simulate from the our project, our case study from the journal. So I cannot find the unit procedure we need, and I cannot find the input we need to in order to design the process. I don't know. It's only happened to my Superpro Designer application that I can't find any. Oh, the unit procedure I need is the chromatograph affinity chromatography, and the input is not registered in the Superpro design. So, and I try to search from the internet, and I still can't find that the data I need to register the input in it. How to deal with this? Thank you.
Oh, okay. If if the component is not available in the database in the library, you have to register. But to register the new component, you have to check is it the correct, because sometimes we just put the default, the properties is similar to water by default, but it's not. You have to check it. If you put a new component, you have to find the common properties for that component, like for example the boiling point, the melting point, the molecular weight, the what are the things, the common one, the molecular weight. Okay, you have to key in that. Do you have to register the new component? Then you have to key in the database. If you could not find the information, probably you have to find the synonym name for that particular component. So that the solution that I normally give to my student. Alternatively, because if you do not register, you cannot get that component generate in the simulation in your and be the output in the stream of that unit operation. So then you have to register for that. You have to register from the beginning, okay, in order it to come out until the end. If you do not register from the beginning, you won't be able to see that component at your on your particular unit operation. Okay.
Okay, so the problem I found is that uh, I can I found the CIS number from the internet, but I didn't find the formula. What is the formula means in when registers the component?
Okay. Because
Do
I don't
you know
have,
about that?
I could not open my Superpro Designer in my laptop. So actually, what is the name of that component actually?
Equine chorionic gonadotropin, or ECG, or it's called, the common name is, I think I'm gonna forget.
Oh, equinon is if like what can I say? Like enzymatic product enzyme, it a bit difficult actually to register there, because I think it could not generate because of they don't have the four element, which is they have carbon, hydrogen, oxygen, nitrogen, but they don't have the empirical formula. That's why it could not be generated there. Okay.
Oh, so I think I cannot try. I cannot design the process.
I know equine quieter, what's the name? Exanthema, right? ECE. Yeah. I did.
ECG, ECG,
ECG. Because
or the. Oh,
when
sorry.
I when I Google here is I think it could not key in there. So you have to find alternative alternative component that's similar to that component. Then you can, if it has empirical formula, so you can use in the simulator.
Okay, thank you.
Yeah.
Okay, thank you. Any more questions? All right. I also see from the list of participants that apart from students from ITB, you also have students from other universities as well. I'm not sure there. I saw students from, I saw somebody from UE. If you want to ask questions, you may ask questions. From other institutions, you may also ask questions. If you want to ask questions, we still have some time left. Hafiz Suhairi. So Hafiz Suhairi, if you want to ask question, you may unmute your speaker and ask directly to the speaker. Hafiz Suhairi, are you okay? So he has lowered his hand, meaning to say that he has no more questions. Okay, are there any other questions from the students or from the participants? So if there are no further questions, I think that I will wrap up this discussion. To Dr. Zun, it is a very fruitful discussion. It's a very fruitful discussion that we have this morning. That's basically our bioengineering students. They are still in their third year. They are having these principles of bioproduct separation that in their case study, they have to design specific separation processes depending on the 4 stages. And then, as you mentioned before about the project design, they also have this, all students are required to do what we call as final year project preliminary design for bioproduction systems. So in that course, in that particular course, students work in groups to design a bioproduction system. So they have to design from a very beginning, from the upstream processes to the downstream processes, and they also have to calculate the economic assessment and also the biosafety and everything. So it's like, I think it's similar with the project design that you mentioned. So they really need this Superpro, because what students normally do that they calculate manually. Very few students that they can use Superpro very efficiently, and some students they use Superpro and then compare with the manual calculations. So it would be good if the students can have a good understanding on Superpro, that they can at the end compare the results of their manual calculation and then compare with the Superpro, because what normally students do, they just use Superpro to draw the process flow diagrams. But some students who have a very good understanding about Superpro, they also do the calculation to check on the material balance, and also to calculate the capital investment, the production costs, and also the environmental impact, because they also have to include that biosafety aspects and also the economic assessment in their report. But if I can see here that Hafiz Suhairi still raising his hand. Hafiz Suhairi, do you still want to ask questions before? No? Is it a yes or is it a no, Hafiz Suhairi? Do you still want to ask questions? All right, I assume that it is a no. So it is very nice that when you explain to us about Superpro, and then you also give us the link on how to use Superpro for beginners. At the end, it's about exercises. So I hope that students, after having a very insightful presentation from Dr. Zun and having given the link to get to use with this Superpro for beginners, so you can start doing exercises, and then hopefully that you can apply this Superpro not only for the principles of bioproduct separation class, but also for your final year project. With that, I would like to thank you very much, Dr. Zun, for the time that you have shared with us, and look forward for future collaboration between Institute Teknologi Bandung and also with you in particular, and also in general with the Department of Biotechnology Engineering from International Islamic University of Malaysia. So before I end this session, perhaps Dr. Zun, you want to say something to conclude this meeting this morning?
Thank you very much to Dr. Yusuf and to all of you for your patient listening to me. And I'm sorry because I do not give you the real simulation through the Superpro Designer, but I'm sure you can try yourself through the tutorial, through the YouTube link via the Superpro Designer website. I'm sure will be helpful for you, but I will try my best. If you have any question, you can let Dr. Yusuf tell me or email me. I try to help if I can help. So thanks again. So good luck to all of you. Okay, thank you.
All right, last but not least, I would like to seek the cooperation from the students. You may unmute your speakers and give a big round of applause to Dr. Zun.
Thank you, Dr. Sun.
Thank you, Dr. Zun.
Yeah. Thank you very much. Thank you very much, Dr. Zun. So everybody, Dr. Zun, so you are allowed to leave the meeting. And for the students, other participants, you are also allowed to leave the meeting. And I still would like to be in touch with the students for this course. I would like to discuss for a few minutes regarding on your course. Okay, again, thank you very much, Dr. Zun, and all other participants. You are allowed to leave the meeting. Thank you very much.
Thank you, Dr. Yusuf.